Welcome back, everybody. Thanks for gathering around the telescope again with me. Just going to expand here about that website that I shared, the latest supernova, and I thought it was pretty important to also include in this post the different types of supernova that go off, so that when you're looking over there on the left-hand column and they identify what type of supernova is, you kind of have a basic understanding of what the different types of supernova are, how they're caused, and what they kind of look like. I need to do one addition here. I'm going to put some light curves into the post, so of the different types of supernovas, so you can gradually see how the light bursts forth and then how it either gradually or suddenly comes down very quickly. And so I'll put those graphs in for you. But if you haven't figured it out, like I said, I love supernova. I am sharing some references that I've read, and books that I've enjoyed. Some of these books I have on my phone in my app. So you can see that there. And we will go back to my library. And I'll just show you. For example, I have some right here. The one I'm reading right now is the MIT Press Essential Knowledge Series called Supernova. And you'll kind of see it come up right there. And there's the text, and I'm on page 459 of 978, and we'll keep reading that. Thoroughly love that book. I've included here. These are some of the ones that I've done. I love studying stellar life and death. This one by The Life and Death of Stars by Kenneth R. Lang came out in 2013. It was a really good read, good foundational knowledge there. Extreme Stars on the Edge of Creation by James Cowler, a little older now, 2001. So it's about 25 years outdated. There's been new knowledge coming in, but again, just a really good foundation. I'm going to mention, I've put the links here to Amazon for these books. I don't get a penny out of this. I don't have any affiliation with any of these authors, these publishers, or anything like that. I'm just doing it there so you can get the synopsis of what the book is about if you want to go there and take a look. If you want to buy them, that's great if that's what you want to do. So this one, The Observer's Guide to Stellar Evolution, is a wonderful book. Again, older, 2002, talks and discusses about stellar evolution, how stars are formed, born, grow, live, and die. Good book, very practical. Practical guide for how you can observe different stars in different stages that are out there right now. And we'll talk about that in a minute too. This one, Unlocking the Secrets of White Dwarf Stars, wonderful read. Again, came out 2014, 11 years old, still pretty, 12 years old actually, still pretty relevant. Some things we've learned some more of, but again, foundational knowledge here. The Supernova Story, this is 2022 by Lawrence A. Marshall. It's the one I just showed you that I'm reading. Really like this book, very basic, very easy to understand. This is probably the first book that I would get if I was wanting to learn more about supernova. I've gained a lot of insight and understanding on the life and death of stars from these, and from a lot of online studying too. So let's talk about these most powerful events in the universe, a star blowing itself up in pieces. I feel it'll be a good review for both myself and for anyone newer to the hobby. When astronomers spot a new supernova and it shows up on latest supernova, one of the first things we usually ask is, what type is it? And no, that's not just scientific nitpicking. The type tells us how the star lived, how it died, and what kind of cosmic behaviors and leftover it's going to leave behind. At the highest level, supernova fall into two big families, okay, based on what we see in their light curves. The two main supernova families are Type 1 and Type 2. In Type 1 supernova, there's no hydrogen present. You can see that in the image here. If hydrogen is missing from the spectrum, we know we're in Type 1 territory. That tells us that the outer hydrogen layers have already gone before the explosion. The star, as it goes through its red giant phase and ends its life, pushes that outer envelope of hydrogen, and thus it isn't present when the star explodes as a Type 1a or Type 1b or Type 1c supernova. Okay? Type 2 supernova, hydrogen is present. If those hydrogen lines are clearly visible as we look at the spectrograph on these, we're looking at a massive star that still had its outer hydrogen envelope attached when it died. That one detail, hydrogen or no hydrogen, tells us a ton about the life story, the star's life story, so to speak. Again, type 1 supernova, no hydrogen. They're split into subgroups based on other elements we see or don't see in them. So a type 1a, this is a white dwarf detonation. It's probably the most famous one. You can see here in this image, this artist rendition, a white dwarf star that's gone through its phases, shed its outer layers, basically is a carbon, oxygen, magnesium, silicon based core left, about the size of the Earth, but the mass of the Sun. It has a companion star, and it's rotating around that companion star, and it's drawing mass off that companion star onto itself. Sometimes as the white dwarfs do this, they will periodically shed some of that mass in a nova eruption. It's not supernova, it's just a brightening. It sheds off some of that mass, but then it will continue to suck more and more mass off of that. As it packs on that mass, pressure and temperature are going to climb within the white dwarf until carbon fusion ignites uncontrollably when the white dwarf reaches what's called the Chandra-Sarkar limit. Chandra-Sarkar was a wonderful astronomer who figured this out. So when a white dwarf gets to the mass of 1.44 solar masses, when it gets to that point, the white dwarf becomes unstable and begins to contract on itself. This in turn releases a gravitational energy which causes the star to heat up further. As a result, carbon and oxygen in the core ignite, and silicon and nickel are produced in a nuclear burning reactions. Finally, a burning wave in the form of a detonation or a deflagration front passes through the glass sphere, and the star just explodes. Okay, boom, as you can see here. The entire white dwarf here detonates in that thermonuclear explosion. There's nothing left behind here. A key fingerprint, a strong silicon absorption line in the spectrum. These are incredibly important, type 1As are. They explode at nearly the same brightness level across the universe and in all galaxies. They make them what's called the standard candle, allowing us to measure distances across the universe by astronomers today. The next one is a type 1b. It's stripped, but it's not bare. These are different. A type 1b is not a 1a. A 1a comes from a white dwarf. A 1b is going to come from a massive star that's lost its hydrogen envelope. Usually it blows it away, and it's blown away by strong stellar winds from the star, or it could be pulled off by a companion. But usually it's blown off by stellar winds. What we see in a type 1b, which I have in the middle here, is there's no hydrogen. You can see strong helium lines. You can see that in the image. And then you're going to have carbon, oxygen, silicon, and irons present there too. The core still collapses like other massive stars. It just does it without the outer hydrogen coat, so to speak. A type 1c, also, it's not a white dwarf. It's a massive star. These are basically more radical versions, the hippie version, so to speak, of the type 1bs, their cousins. These stars have lost both their hydrogen and helium envelopes, so their spectra will lack both the hydrogen and strong helium lines when we look at them with the spectrograph. These are some of the most dramatic stellar deaths and often linked to gamma ray bursts when conditions are just right with these stars. Basically, going to be really big explosion here. Type 2 supernova. These are where hydrogen is present. And you can see, look at the image here, what it looks like. These are the more classic, what we think of the classic supernovas. These stars are usually 8 times the mass of the sun or greater. They have to fall into this category. They fuse heavier and heavier elements in their cores until they build up an iron core. And the iron can't produce energy through fusion. Think of it this way. Once a star of this massive size has consumed its main supply of hydrogen and helium at the end of its life, carbon, the ash of the helium fire, that's what's created as it burns helium, ignites in its core. The temperature rises to billions of degrees Celsius. Neutrinos are produced in large numbers. Finally, over a period of just a few years, the star produces elements of increasing atomic weight: neon, oxygen, silicon, and finally iron. Iron is the last of these, and since iron atoms cannot undergo further fusion, the reactor turns off. It's extinguished. Here's another way to think about it. In these massive stars, the fusion process can restart at the end of the red giant phase. So as it burns off hydrogen and helium and it expands after burning through those phases, and I see a little typo, so I'm just going to grab that real quick. After burning through the hydrogen and helium layers, when the helium runs out, the core collapses, and that pressure and heat causes, because there's enough mass present, the temperature of the core gets hot enough so that it ignites carbon fusion. Just as before, the reignition of fusion prevents any further collapse. Okay, star stabilizes. The third round of fusion creates a nuclei of magnesium, neon, sodium, and aluminum. The star swells even more and becomes a red supergiant at that point. So it's a red giant in burning off those hydrogen and helium layers, and then because it's so massive, as it begins to contract, that heat and pressure ignites the carbon begins to build, the star stabilizes, then produces these other elements. Just as before, this reignition of the fusion prevents any further collapse at this part. This third round of fusion creates nuclei, like I said, magnesium, neon, sodium, and aluminum. Think of Betelgeuse and Orion and Antares in the constellation of Scorpius. You have VY Canis Majoris in Canis Major, which a 14-inch greater telescope can view that currently at magnitude positive 8.93, and it actually has a companion star with it at magnitude 10.34, which a scope that size will get. And I'm going to add just a quick finder at the bottom of the article. It won't be in the video here, so you'll have to go to EadsyAstronomy to get that. But you can actually look up in the night sky right now if you want to hunt that down and say you've seen a progenitor of a coming supernova. We have Mu Cephei, the Garnet star in the constellation of Cepheus, or UY Scuti, located in the Scutum constellation in the summertime. And that one is known as being the largest known red supergiants out there. These ones are. Then as the star, just getting back on track now, a little divergent there. Then as the star forms into a red supergiant, this is followed by further collapse, reignition, and fusion for a fourth round, which creates silicon, sulfur, and argon. The star goes through several stages of collapse, heating, and expansion, and fusion, with each round of fusion continuing for less and less time until the star is layered up with different layers rich in the elements that it has fused together and with a core of solid iron. This image will show basically what happens with a 20 solar mass star and how many years it takes to go through these stages, kind of estimated. Hydrogen burning to helium, about 7 million years. Helium burning to carbon, 700,000 years. Carbon to oxygen, about 600 years. Oxygen to silicon, about 6 months. And then silicon to iron, that's going to happen. That's going to burn that stage in 1 day. And when it gets to that point and iron can't ignite, the core is going to collapse, and that's going to happen in milliseconds, a quarter of a second. And then that's when the star is going to explode as a supernova. See, finally, when iron's produced, that gravity that keeps wanting to condense, and then the star reignites the fusion in the next stage, and then condense, reignites because of the pressure and the heat. Finally, when you get to iron, that can't happen. Gravity wins, the core collapses, boom. Okay? The result is usually we're either left with a neutron star or a black hole, and then from here we'll break things down to how the light fades over time. With different types of type 2 supernova, with a type 2 P, this is known as the plateau. This is the most common type 2 supernova. After the explosion, the brightness levels off for weeks to months, creating a plateau in the light curve. The plateau happens because hydrogen in the outer layers are slowly recombining and releasing energy. It's a nice steady fade before finally dimming for good and going out. That is what some astronomers feel Betelgeuse is probably going to do when it blows. Type 2L, the linear fader, these skip the plateau and just fade steadily and more linearly after peak brightness. It's So they do that, and then they kind of just go off. They're still hydrogen rich, just a different envelope structure and mass loss history before the explosion. Type 2b, the shapeshifter, this one is actually really cool. Early on, the spectrum will show hydrogen, so it's going to look like a type 2, but later the hydrogen lines weaken and it starts to resemble a type 1b. The translation, the star probably only had a very thin layer of hydrogen left when it exploded. It had blown off part of that, but kept just a little bit. That's why we're seeing it. That's why we call that a 2b. Kind of looks like a shapeshifter. We got the type 2N, the interaction show. The N stands for narrow spectral lines. These happens when the supernova blast wave slams into dense gas that the star has shed earlier in its life. The interaction creates a narrow emission lines and can make the supernova shine extra brightly for a long, long time. This is less just an explosion and more of a cosmic crash scene. Think of it that way. The extreme and exotic explosions that happen out there, not all stellar explosions fit neatly into standard boxes. You have what's called the hypernova, superluminous supernova. These are ridiculously bright, sometimes 10 to 100 times brighter than the typical supernova, and most supernovae will outshine their host galaxy, just so you know. So these things are bright. Often they're linked with type 1c events and occasionally with gamma ray bursts. We're talking serious cosmic fireworks here when a hypernova goes off. There's called the instability supernova, a theoretical and possibly rare explosion of extremely massive star. Instead of leaving a remnant behind, the star basically completely destroys itself, scattering its material across space. There's no neutron star, no black hole. It's just wiped out. It's just gone. You then have what's called the kilonova. It's not a star death, but a stellar collision. This one's different. A kilonova happens when two neutron stars that are rotating around each other and their orbit becomes closer and closer until they finally merge. And when they merge, the collision forces heavy elements like gold and platinum and produces a short-lived but powerful glow out there. So if you've ever worn gold jewelry, had a wedding band or something like that, think a neutron star crash for that one. Why does this matter? Each supernova type, when you look on it on the latest supernova site, tells a different life story of that star. Type 1a, that was a star about the mass of our sun, maybe just slightly a little bit bigger. It's gone through its life. It's formed a white dwarf, and it's an exploding white dwarf. It's usually stolen material from a companion, or two white dwarfs can merge. Type 1b, 1c, 2, these are massive star collapse. This is what we typically think of as a supernova. 2n, the explosion meets earlier stellar outbursts. So the star has shredded enough gas out there that when it goes supernova, the explosion meets that earlier stellar outburst and kind of makes it really bright. Kilonova, neutron star merger. Boom! Okay? When we read these spectral fingerprints, we're not just classifying the explosions. We're doing stellar forensics here. Figuring out how the stars live, lose mass, evolve, and ultimately return their material to space so future stars, planets, and maybe even life can form. Think about it, the iron in your blood, the calcium in your bones, all these have been a result, the oxygen we breathe, from supernovae that have gone off in the past. So next time you see news of a supernova discovery or go to the latest supernova and you look down that left-hand column and you see what the type is stated, know that it's just not that label. It's the star's final autobiography written in light of what type of star it was and how it lived and how it dies. I hope you find that useful. Hope you can use it. Going to put a few more things in here. I want to show you how to get to VY Canis Majoris right now. I'll put that at the end down here. Got to put some light curves in so you can see that on the post. But keep looking up. I hope you have clear skies. We don't. Kind of cloudy, snowy, cold night here in northern Utah, so hopefully that clears up. Still would like to get some lunar observing in before we move into new moon in a couple weeks. Thanks for joining me. Have a great time. See you next time around the telescope.